Hello guys, and welcome to this video. So this is the first video where we'll start exploring the practical application of the theoretical knowledge we've been learning. We want to sketch the Nyquist plot and determine the stability of the unity feedback system that is given by this transfer function g of s equal to k divided by 1 plus t1s and 1 plus t2s. So if you were with us in the last video, we established that this kind of system is called type 0 system. It's called type 0 because s has the power of 0. Okay, the term s, it does not occur in the denominator, or in other words, it has a power of 0. The s raised to the power of 0 is 1, therefore you have it like this. So let's solve this problem. So I'm going to follow a stepwise approach to drawing the Nyquist plot. Anytime you want to draw the Nyquist plot, you need to follow this step. So the first step is to check whether the system is in standard form. So is the system in standard form? Yes, the system is in standard form. It's in standard form because it is expressed in k into 1 plus t1s and 1 plus t2s. Standard form is whereby the factors are expressed such that we have 1 then plus time constant. Is that okay? Before s, then 1 plus time constant before s, and so on and so forth. Is that okay? It must always be like this in standard form. So if the check for standard form is complete, then the next thing we want to do is to also make sure that the time periods are arranged in decreasing order. So t1 is bigger than t2, and if there is a t3, okay, it's going to be bigger. T2 is going to be bigger than t3, t3 is going to be bigger than t4, and so on and so forth. So that standard form, you arrange it in standard form, making sure that t is decreasing as we move across the factors. Okay, so the next one is to put s equal to j omega. So when you put s equal to j omega, your g of j omega is now going to be k into 1 plus, you have j t1 omega, okay, or j omega t1. Let me just put it like j omega t1. Then you will now have 1 plus j omega t2. So we have replaced s with j omega. So that's the next step. Then the step following will now require us to calculate the magnitude and phase of g of j omega. So you could label this, let's say I label this as equation 1. So I want to calculate the magnitude of j omega. So the magnitude of j omega is going to be, so we are dealing with complex numbers, okay? So when you're calculating magnitude of this stuff, you can calculate it in one position. So the magnitude of the numerator, first of all, magnitude of k is just simply k. If it was minus k, it would become k, okay? Because magnitude is like absolute value, or magnitude is the square root of something square, so you just have k there. Then in the denominator, the magnitude of this complex number is the square root of the sum of the squares of the real and the imaginary part. So 1 square is 1 plus the imaginary part is omega t1. So omega t1 square is going to be omega square t1 square. So you're going to multiply the magnitude of this one by the magnitude of this one eventually to get the magnitude of this whole denominator. So magnitude of the numerator is k, and magnitude of the denominator is magnitude of this complex number times magnitude of this complex number, which is going to be 1 plus omega square t2 square. Is that okay? So if you want to find the phase of j omega, I can call this equation 2 for magnitude. So the phase of j omega is going to be, okay, so the phase of j omega, so we have a combination of complex numbers in this form. So how do we find the phase? So I'm just going to write, replicate the complex number here. We have k all over 1 plus j omega t1, and you now have 1 plus j omega t2. So d is a complex number. For any real number, okay, the phase of any real number, okay, is 0 degrees. So if the real number is positive, the phase is 0 degrees. If the real number is negative, the phase is minus 180 degrees. Take note of that. If the real number is positive, the phase is 0 degrees. If the real number is negative, the phase is minus 180 degrees. Okay, that's when we are dealing with control system. So the phase of K is going to be what? 0 degrees. Then the phase of this guy over here is going to be, or the phase of the product of two complex numbers is actually the sum of their individual phases. I come again with that. The phase of the product of two complex numbers is the sum of their individual phases. So I'll use one big phase to capture the phase of these two. So the phase of this one alone is tan inverse of this value divided by this value. This value divided by this value is just, that's going to be tan inverse of omega t1 divided by 1 is omega t1, then plus tan inverse of omega t2 divided by 1 is going to be omega t2. So the phase of the denominator, which was actually the product of two complex numbers, is now the sum of their respective phase. So we now have phase of numerator divided by phase of denominator. So it's going to be one combined phase, and that's going to give me, when you're dividing phase angles, okay, they're just like vectorial angles, you subtract. So 0 degrees minus the sum of these two, which is tan inverse of omega t1, okay, plus tan inverse of omega t2. So eventually we are going to find it as g of j omega. I'll do away with this cap. You just have 0 minus this whole stuff will be minus tan inverse of omega t1 minus tan inverse of omega t2. So I hope you understand that, how to calculate the phase. So henceforth, when we are calculating the phase, I'll just calculate the phase of the numerator 0, then I'll subtract all the phases in the denominator, the individual phase. So phase of the numerator being 0 degrees, 0 minus, then phase of this one is minus tan inverse of this, then minus tan inverse of this particular one. Okay, so I hope you get how to calculate the magnitude and the phase. So the next thing is, you are now going to consider asymptotic conditions of magnitude and phase. So you consider asymptotic conditions of magnitude and phase. So when you want to test or when you want to draw the Nyquist plot, after following all these steps, you've gotten your magnitude and your phase, right? Our magnitude is this, and this is my phase over here. So the next thing is I'll apply asymptotic conditions to the magnitude and phase to give me an idea of how the graph will look. So this might be the last step for many of you. So let's find out, applying asymptotic conditions. So our magnitude was calculated as, magnitude of j omega was calculated as k all over the square root of 1 plus omega square t1 square, then square root of 1 plus omega square t2 square. So if you apply asymptotic conditions, okay, to this particular formula, the asymptotic condition is you apply is when omega t, when the product of the frequency and the time constant, first case, it's when it's far less than 1. So when it's far less than 1 is another way of saying when omega approaches 0. So when omega approaches 0, how will the magnitude be? Or how would the magnitude be? So we'll see that the magnitude of g of j omega, okay, is going to be approximately, or the limiting value of the magnitude as omega approaches 0 you see that this term will be very small, so you can just neglect it. 1 plus 0 and 1 plus 0. Okay, so this term will approach 0 and this term will approach 0, so we'll just be left with k all over square root of 1 times square root of 1, which is k all over 1 times 1, which is k. So the limiting magnitude of j omega as omega approach 0, okay, or as omega, if omega t is far less than -1, you're going to get k. Okay, that's k. So you're going to apply the reciprocal this time around when omega t is far greater than 1. That's another way of saying when omega is approaching infinity. So when omega is approaching infinity, you will find the limiting value of the magnitude as omega approaches infinity. That's your g of j omega. Okay, so if you find that limit as omega approach infinity, you will discover that omega square, which is infinity square times anything square, is still infinity. 1 plus infinity is infinity, and the square root of infinity is still infinity. The same thing will happen here. In fact, you have infinity times infinity, which we can also, although it's indeterminate, but we can approximate to infinity. Eventually, you'll be left with k all over infinity, which is actually 0, because when the frequency is very large, the bottom will be very large, so we can just approximate it to k over infinity, which is equal to 0. So in other words, the limiting value of the magnitude when the frequency is very large is going to be 0. So we are going to do the same thing to the phase. Okay, so just by the side of this place, I should have written the formula for my phase of j omega. That's g of j omega. So the phase we got was minus tan inverse of omega t1. Let me demarcate it. And minus tan inverse of omega t2. Remember, we're in asymptotic conditions of magnitude and phase. Okay, so we're considering limits. So we'll also consider what happens when omega t is far less than 1, or when omega approaches 0 itself. So when omega t is far less than 1, how will the phase be affected? You discover that the phase, okay, angle, the phase angle will be approximately, that's the limiting value of our phase angle, that's g of j omega, as omega approaches 0, is going to be minus tan inverse of 0 minus tan inverse of 0, which is still 0. Tan inverse of 0 is 0 and tan inverse of 0 is 0. So we'll repeat the same thing that we did for this particular place. Okay, so when omega t is far greater than 1, or when omega approaches infinity, so how will the phase change? We are going to find the limiting value as omega approach infinity of g of j omega. So that will be minus tan inverse of infinity minus tan inverse of infinity. Tan inverse of infinity is 90 degrees, so you have minus 90 degrees minus, and that tan inverse of infinity is 90 degrees, which is going to be minus 180 degrees. So we can see that under asymptotic conditions, when the frequency is almost infinity, the magnitude will be 0, but the phase will be minus 180 degrees. Then if the frequency is small, the magnitude will be k, right? The phase will be 0. So how do we interpret this on a graph? So this is how we interpret it on a graph, and I'll teach you how to be sensitive when drawing graphs like this. So when you're drawing graphs like this, remember to label in the clockwise direction. You have 0 degrees, minus 90 degrees, you now have minus 180 degrees, and you now have minus 270 degrees. This is your polar axis, or your imaginary axis, and this is your real axis. Now when you're drawing contours, remember you draw the contours as, okay, contours of magnitude versus phase. Okay, for every magnitude there is an associated phase. Now let's check the first magnitude. That's the first magnitude when our frequency is 0 or approaching 0. That magnitude is k, but the phase is 0 degrees. So all we just need to do is to stretch from here to here, k. And since the phase is on 0 degrees, there is no elevation or depression. Okay, so it's just going to rest on this place. So I can simply say that k is here. Okay, it's on the 0 degrees line, and let's say from here to here is k. or we can just call these points, K here. So when omega tends to 0, our amplitude is K and our phase is 0 degrees. Is that okay? So another asymptotic condition we got was when omega is close to infinity, our amplitude is going to be 0 and our phase is going to be minus 180 degrees. So how do you actually represent this? So I know it might be strange to most of you, but the phase is actually minus 180 degrees, okay, and the amplitude is 0. So what they're just trying to tell us is that our graph or our contour originated from this point and it started following this path. It followed this path, okay, then at minus 180 degrees it now started towards minus 180 degrees, now started spiraling into the origin, and eventually this is when W was close to negative infinity. So it confirms that at infinity the magnitude is 0, okay, and the phase angle is minus 180 degrees. So this is the sketch of the Nyquist plot for this system. So this is it. That okay? So if you check the first diagram, you'll discover that in one of the examples I gave, perhaps there was a Nyquist plot that looked like this when we were analyzing Nyquist stability criteria. So for any type 0 system of this form, the Nyquist plot will always look like this, and the solvent is the justification. So at this point, we've come to the end of this video. Now I want to do something else, and I'll tag it as optional. What I want to do now is optional, but if you understand what I want to do now, it's going to really help you, because I want to generalize some formulas that will help us in the remaining parts of discussions. So sometimes you might be interested in what happens here. What is the value of the magnitude at this point? Okay, what's the value of the magnitude at this point? Okay, and what is the value of the frequency at this point? So we're actually interested in what happens at this point. So how do we find it? So if you want to find it, you need to actually consider your G of J omega. Okay, your G of J omega. At this point, you can actually submit, okay, for this question, you're done with this question, but I want to make some important generalizations, okay, that will help us. Now, if you want to find the value of this point, that's the frequency and the amplitude of G of J omega at this point, which are very, very important. You have to separate your G of J omega into real and imaginary parts. So my G of J omega can be separated into real and imaginary parts as follows. So we have our K divided by, you have your 1 plus J omega T1, okay, and 1 plus J omega T2. So if you want to separate it into omega real parts, what we want to find is points of intersection. So where does the contour intersect the real axis and the imaginary axis? That's what we want to determine. So you have to separate this one into what a real and imaginary parts, and to do that you need to rationalize. So in rationalizing, you have times 1 minus J omega T1, that's multiplying by the conjugates, and 1 minus J omega T2 all over 1 minus J omega T1, 1 minus J omega T2. So let's look at the simplest way to evaluate this. So you have your G of J omega is going to be K into 1 minus J omega T1. Okay, let's just do the multiplication straight on. So 1 times 1 is going to give you 1. Now I'm not going to do the normal this times this times this. When I do 1 times 1, the next one I'll do is this times this. So J omega minus j omega t1 times minus j omega t2. So you need to understand that j times j is minus 1. Is that okay? So irrespective of the fact that this times this is going to give you a plus, minus times minus will give you plus, minus j times j will give you minus 1, omega times omega will give you omega square, and t1 times t2 is going to give you t1 t2. So I did this times this first, then this times this, then I can now do the cross product. 1 times, sorry, minus this one times 1 will give me minus j omega t1, and 1 times this one will give you minus j omega t2. Is that okay? So I hope you understand. You can try to settle down and expand this one on your own and see what you get. So in the denominator, something interesting happens. I'll multiply this by this and multiply this by this. So when you're multiplying complex conjugates, you just need to know that you will get real numbers. If I'm multiplying a plus ib by a minus ib, I'm going to get a squared plus b squared. So we have difference of two squares and sum of two squares. Sum of two squares is when you express the individual factors in form of complex numbers, but difference of two squares you express it in form of real numbers. So that's exactly what will happen here. This one and this one will give me 1 square, which is 1, plus this and this is going to give me omega square t1 square. Then if you multiply this by this, which is sum of two squares, you get 1, then plus omega square t2 square. That's what you get. Okay, if you do the multiplication by yourself. So just try to follow the law I established on sum of two squares. So at the end of the day, what you'll be having is your g of j omega is going to be, you have k into 1 minus omega square t1 t2. Then if you capture these two together, you get minus j omega into t1 plus t2. All right, then everything all over 1 plus omega square t1 square, and we now have 1 plus omega square t2 square. I can just call this 1 plus omega square t1 square times 1 plus omega square t2 square. I can call it delta as the denominator. So at the end of the day, my g of j omega is now going to be what? If you separate into real and imaginary parts, you have k into 1 minus omega square t1 t2 all over denominator, that's this whole stuff, and you now have minus j omega into t1 plus t2 all over denominator. Is that okay? Where the denominator is this whole expression. So we have successfully separated our g of j omega into real and imaginary parts. Now to find the vertical intersections, you need to equate the real parts to 0. So equating the real parts to 0 is going to give me vertical intersections, and by vertical intersections we are trying to talk about the point where this contour intersects this vertical axis. So we'll be able to find that frequency, and eventually we'll be able to find the amplitude. So equating for vertical intersections, you equate the real parts of g of j omega to 0. So the implication, what we had was k into 1 minus omega square. So you have t1 t2 all over the denominator that we had is equal to 0. So why I'm putting the denominator as delta is that it doesn't matter, as far as we've equated it to 0, only the numerator will be equal to 0. That's k into 1 minus omega square t1 t2 be equal to 0. So eventually, if you divide through by k, you have 1 minus omega square t1 t2 is equal to 0. So this implies that what? Omega square is equal to 1 divided by t1 t2, then implies further that omega is going to be 1 divided by the square root of t1 t2. So the frequency at the point of intersection, vertical intersection, is 1 divided by t1 t2. This frequency is very important, very, very important, and this frequency is called phase crossover frequency. Now, I don't know if we have learned about phase crossover frequency in the past before, but I think we have in the first or in the second video where we studied phase margin, gain margin, phase crossover frequency, and gain crossover frequency. Now, for a type 0 system, the phase crossover frequency WCP is actually 1 divided by the product of the square root of, or the square root of the product of the time constant. So you need to memorize this formula. Is that okay? So let's find the magnitude. Okay, the magnitude of our g of j omega at this function. So recall that our g of j omega, that's the magnitude of g of j omega, is given to us as k divided by the square root of 1 plus what? Very good. Omega squared t1 squared and root 1 plus omega squared t2 squared. So all you just want to do is to substitute, put omega equal to 1 over the square root of t1 t2. Now these calculations is getting big and boring, but trust me, you're only going to do it this once, and that will be all. And I'll show you how to apply it in upcoming calculations. So let's just bear and solve it to the end. So you have your magnitude of g of j omega to be k all over square root of, you now have 1 plus omega square is going to be 1 all over t1 t2. Okay, when you take omega square. So if you put omega square by this particular stuff, t1 square is going to cancel out 1 t1 in the denominator, leaving us with t1 all over t2. So the same thing will happen for the other square root. You have 1 plus, if you put omega square by t2 square, you're going to have t2 over t1. So in solving further, you have k all over, multiplying, you have t2 plus t1 over t2, then root t1 plus t2 all over what? T1. Is that okay? In solving further, you're going to have k all over root t1 plus t2 divided by root t2 multiplied by root t1 plus t2 all over root t1. Okay, when you apply sort, this gives me k all over. The product of this one will give me root t1 plus t2 square, which evaluates to t1 plus t2. Everything divided by, then if you multiply this one, you get root t1 t2. So at the end of the day, the magnitude of g of j omega, okay, magnitude of j omega at that particular frequency, that's our phase crossover frequency, is going to be, if you take this one to the numerator, you get k root t1 t2 all over t1 plus t2. So this is what we call our alpha, okay, or the magnitude at our WCP. Now, if you remember in the last video when I was explaining gain margin, and I told you that if you have something like this, your alpha, and this is your unit circle, for instance, your alpha is this distance from here to here, okay, the magnitude from here to here, okay, and I told you that this point, the frequency here, is called your WCP, your phase crossover frequency. So a phase crossover frequency is the frequency whereby our phase of our complex number is minus 180 degrees. Then alpha is the value, or is the magnitude of our g of j omega at that frequency. That's this distance from here to here. So anytime we want to calculate gain margin, all we just need to do is take the reciprocal of alpha, and alpha is this particular value over here. So if you're asked to calculate gain margin, remember the steps is, first of all, you need to calculate the phase crossover frequency, which is this one. After calculating the phase crossover frequency, you now calculate this value of alpha, which is this one. Then you take the reciprocal and your gain margin is 20 log the reciprocal. Okay, and that's how you get your gain margin. So this is the importance of this calculation. So I want to round up this particular calculations by establishing an important formula. Now what we learned is that when we have g of s, whenever we are giving a g of s equal to 1 divided by 1 plus s t1 and 1 plus st2, we're able to discover that our WCP, that's our phase crossover frequency, is given to us as 1 over the square root of T1 T2. Then our phase crossover frequency, there's something not so right with my writing material. 1 over the square root of T1 T2, that's the phase crossover frequency. Then the magnitude of j omega at this frequency is given to us as k root T1 T2 all over T1 plus T2. That's going to be the magnitude. Okay, and for this particular graph, I'll represent this place as W is equal to 1 all over root T1 T2. Then this distance from here to here is the magnitude, is going to be k root T1 T2 all over T1 plus T2. Okay, that's this height from here to here. So that's what it means. So this is for zero order system. Now if you're giving a one order system, okay, I'm not going to show you how to do it now because of time. So for one order system, you can actually generalize. Sorry, this is a k. So for one order system, generalization is that you have k all over s raised to the power of 1. Then you now have 1 into st1, 1 plus st2. Let's say you have a one order system like this, which is mostly what you'll be encountering in exam. Now the crossover frequency, WCP, is also going to be 1 all over root T1 T2. But what we change is this guy, the gain at this crossover frequency. Sorry, not the gain, the magnitude of g omega. So the magnitude of g omega at this particular frequency, omega Cp, is going to be, instead of k root T1 T2, is going to be k T1 T2 all over T1 plus T2. So what I just wanted to establish is, when you have a system like this, okay, when you have a system like this, you have to memorize these two forms. For one order, memorize the crossover, that's the phase crossover frequency, and you need to memorize your alpha value. So for this system, this is just, I mean, this was our Nyquist plot for one other system. Then it means that this place from here to here is actually this magnitude, that's k T1 T2 all over T1 plus T2. That's the magnitude from here to here. Now this frequency is still 1 all over root T1 T2. So when omega is equal to this one, and we have this particular magnitude over here. Is that okay? So with this magnitude, you can find your gain margin by taking the reciprocal of this magnitude. Is that okay? So I hope you understand this. And that will be all for this particular video. I just wanted to establish this because we are going to be using this formula as we progress. So we are going to solve another example in the next video, another possible exam question. So stay tuned and see how we are going to apply this formula to solving the next question. Thank you very much and have a wonderful time.